Okay folks, welcome to our next video in the series on geometric reasoning. As promised, in this video we're continuing with the Hiele levels of geometric reasoning. We are going to look at the last two levels, the level of formal deduction and rigor. And let me just remind you what the argument was in our previous video, is that 40% of learners that go through high school geometry lessons are at most at the third level or level 2 or below. Okay, so if it's below, you can imagine it's more visual than what it is anything other. Okay, so before I start this series, I want to revisit the quote in the last video, the end of the video, where we quoted Pierre van Hiele. He said a definition is a concept is only possible if one knows to some extent the thing that is to be defined. Now folks, that's huge, because in our school curriculum we usually start the other way around. We start with a definition, or we start with a theorem, and then we apply it. Okay, and the Van Hiele and Hans Freudenthal, who's there on the screen, both maintain that you should have a little bit of experience with the ideas around the definition, and then those ideas constellate and condense in the notion of a definition of a mathematical concept. So just be aware of that as a teacher one day when you teach, that this is actually the ideal way for us to teach mathematics, is to provide that experience, define and work. And you'll see in the phases of learning, which is the next video, we will model that as a practice. Okay, so let's continue. Level 3, which is the fourth level, is called deduction. What does deduction represent? Well, learners go beyond just identifying characteristics of shape and are able to construct proofs using postulates or axioms or definitions that they have formulated up to this point. They know the meaning. Now this is huge again, remember, the meaning of necessary and sufficient conditions. That is big in geometry teaching. What is the necessary and sufficient conditions that makes a quadrilateral a parallelogram? What are the necessary and sufficient conditions that makes a square and a rhombus a rhombus? Now you will see often they overlap the properties, but we can chop some properties away and formally define those two figures. And that happens at the level of deduction. A typical high school geometry course should be taught at this level. Students should be able to construct proofs such as those found in the geometry school curriculum, and be able to see a proof and develop it in more than one way at this level. So there's a perfect example, is Thales' theorem. You can prove that theorem using trigonometry, using analytical geometry, using just algebra. There's lots of ways to prove the theorem, and at the level of deduction, that is the opportunity you should afford learners. We're not giving them the proof. Together, we're looking at the tools we have up to now, the cumulative knowledge we have, and we bring that knowledge in to the geometry space to construct a proof, just like Euclid did. Okay, so learners at this level believe that axioms and definitions are fixed rather than arbitrary. So they cannot yet conceive of non-Euclidean geometry. So at the deduction level, they are quite well versed, or they should be well versed, of the geometry, the Euclidean geometry that happens in a plane. But they still cannot make the transition into things like spherical geometry or hyperbolic geometry and other geometries that exist. Excuse me. Okay, so geometric ideas are still understood as objects that only exist in the Euclidean plane. They might not even be aware that there are other geometries unless you just poke that interest every now and then and say, but is this always going to be true? We're going to look at that when we talk about habits of mind. Excuse me, folks. So let's see what the student can do. The student recognizes and flexibly uses the components of the axiomatic system at the level of deduction. Now the operative word there is this word flexibly. To flexibly use knowledge means you've been afforded the opportunity in establishing and developing the knowledge that you're going to use. Okay, so they use undefined terms, they use definitions, postulates and theorems to argue with at the level of formal deduction. The student can create, compare and contrast different proofs and how those proofs change, even for the same idea. What are different between the proofs and what remains the same, the big ideas, variance and invariance in mathematics. The learner, however, does not compare axiomatic systems at the level of formal deduction. Okay, so suggestion for instruction using formal deduction are as follows. Introduce formal proof as a reasoning tool. Now that's big. That's very big. Formal proof as a reasoning tool means, for instance, you are not going to open the textbook to say, today we're learning about opposite angles of a cyclic quad. This is what the theorem says, this is what its converse says, and this is how we prove it. No. We will start with, to construct the reasoning necessary to construct a proof, we will start by looking at putting relational features in place in a diagram and then work from there. So proof becomes a tool to learn with. Compare a variety of proofs for the same problem. The angle at the center is twice the angle on the circumference is one of those type of proofs that we can talk about when we develop this notion of proof as a reasoning tool. So Thales' theorem there, another perfect one to use. So drawing and construction is key here at this level because it focuses on the relational aspects in the geometry classroom and the geometry riders that we look at. Very big statement that. Okay, and I'll come back to that with an example now. Lastly, there, the geometric language must be fully developed at this level. And then working on geometric specific language is key. Now, the Van Hieles have said that. In the previous video we spoke about it. Every single level comes with its own mathematical register and discourse. Okay, so we want to develop the language that's appropriate at that level. If a child is busy at a level 0 to talk about the similarity or proportionality theorems, it's not going to make sense there because it only goes on the visual. So at the level of deduction, we want this idea of geometric reasoning and using proof as a reasoning tool to be fully developed with the language that is appropriate at that specific level. So before I go to that example, let's just go back to where I said compare a variety of proofs for the same problem, and let's look at Sketchpad. Now if we start with Geometry Sketchpad, and let's talk about the angle at the center is twice the angle on the circumference. Now the theorem says if a chord, oopsie, I did not even draw a chord there, let me just take that away. if a chord or an arc, now that's the arc, that's the chord, what must the chord do? It must subtend an angle at the center of the circle, and also the same chord must subtend an angle that lies on the circumference of that circle. Then the relationship is that the angle at the center is twice the angle on the circumference. Now we know that as teachers. So we are going to talk about working with an activity and putting those relationships. You saw what the relationships were. We talked to the relationship. Make the relationship, foreground the relationship as the thing that is important. The chord does two things. On the same side of that chord, it subtends an angle at the center, and it also subtends an angle on the circumference. Now we want to know more about the angles that are subtended. So I'm just going to color that one in. That's the one we're looking at, and that's the angle we're looking at. So we are going to tell the computer, because as a teacher now, we know that relationship. Okay, so we want to talk about looking at the size of that angle. That size is 44.57, and this size, we tell it to measure that angle, is 89. Now we can at this point tell the computer or the software to calculate the angle at the center divided by the angle that lies on the circumference, and show that, because that is what we want to talk about, that is always going to be true. Okay, so now we're going to look at what conditions, how the conditions change. Remember the big idea? How does the conditions change that I'm working? And with that conditions changing, as I transform the figure, which relationships remain in place and which change. So at this point, I would want to move this B around. Okay, so as I move it here on the circle, I can see that the relationships over here remain intact. Now it looks like those relationships are not working at all. Okay, but then let's continue here. And it's quite clear that the moment we go there, things have definitely changed. Okay, so now the 2 has become 0.66. So now it's ripe to talk about what happened here. And hopefully then the idea of, oh man, we've moved, or sir, we've moved to the other side, the chord, the arc that is subtending the angle at the center. We are now below, we're on the minor arc instead of being on the major arc. Listen to the language development. So we are not in the same segment of the circle. Why? What is a segment? Well, the chord divides the circle into two, a minor segment and a major segment, or a minor arc and a major arc. We are on the major arc here. The moment we move to the minor arc, the relationship is violated. So you can see I'm trying to model the language that we use. And then obviously proof as a tool. Let's talk about that. Now we know that there's something about a circle that we can use. The fact that that line is equal to that line, because both of them are radii. Now we want to prove this theorem. And up to now we have a wealth of theorems using triangles. So you might want to then start talking about the relationship between those angles. How am I going to move from this angle to that angle? And hopefully in that discussion, one would see, or one would, then we just undo that, one would then get to the point where you can say that you want to construct not the segment but a ray, because the ray will finish or has a vertex at B and move through D. Now you'll notice I went to construct, I didn't draw. if I drew it, that ray wouldn't have stayed the same. And now talk about what this affords us. Well, it affords us the use of that as a radius. Okay, and we can see isosceles triangles, we can see exterior angles, and through that exterior angle, the link is established. So affording that cognitive process to take place in the geometry class is what the Van Hieles are arguing is very important, folks. So don't just go to the theorem and put the theorem on the board and prove it. Talk about relationships. What do we know up to this point that we can use to prove the actual theorem? Okay, let's look at that question there. And at this point, I want you to pause the video. Let's just read what it says. It says we have triangle ABC. BM is a median. I can prove that the area of triangle ABM is equal to the area of triangle MBC. Before we go there, let's just talk about the density of the concept, the semantic density of the concept of a median. A median, number one, is a line. Now, you can say a lot about a line, but it's a line with specific conditions. It runs from one of the vertices, in this case B, over to, let me just get my highlighter again, from B it runs where? To the opposite side, but what does it do? It bisects that side. That is what a median does. Now there's more to say about the median, but that's all we need to know for this particular proof. So pause the video, prove that statement, and then come back and we'll see if you're correct. Okay, let's go back to my hovercam and let us see what it is that we want to prove and how we are going to prove that. Let me just get the light ready. Okay, so there we go. We have had that is a median, so we know that these two sides are indeed equal. Now we've got one of two choices. We want to work with area of a triangle. So we can use the area rule in trigonometry, which needs the length of two sides that include a particular angle. So we need the information about those two and that angle, and these two and that angle, and we clearly don't have that information. So we're going to look at an alternative. If we construct from the apex up there, construct a perpendicular. That perpendicular has a height of h. Now we can see, we can use the rule a half base times height. Because why? Well, the height for the smaller triangle is the same as the height for the bigger one. So the area of triangle ABM over the area of triangle BMC, I want to prove is 1 on 1. Then I've proved that they're equal. Okay, so let's have a look. The area of the small one is a half the base, which I pick as AM because it runs from the vertex to the base, times the height, over the other one is a half MC multiplied by the height. Now the heights are the same, the halves are the same, so all I need to argue is that those are the same. So we go, but AM is indeed equal to MC, because BM is a median, and because it's a median, it bisects the opposite side. Okay, so therefore, conclusion, area of triangle ABM over the area of triangle BMC is 1 to 1. So the areas are equal. Now let's just stick there for 1 second. I had a choice of two things that I can use for area of this triangle. There are other theorems that you can also use for area, of the triangle, but I focused on those two because of the diagram. Now, what did we need to know? We needed first of all to know the definitions and the tools that we could use to work with the area of the triangle. Then we had to identify that, listen, we don't need parallel lines here. If we just drop an altitude, that altitude forms the height of the small triangle, which is acute angle. Just look at the density here. And it also forms the height of the triangle that is obtuse angled. I placed them on a ratio. Why? Because I want to show the ratio is 1 to 1, then those will be equal. Okay, and then I applied my area formula, and it got me to exactly the same thing. Okay, so I hope that some of you got to that. Some of you might have used something else to find the area of the triangle. I don't know. Let's return to what the Van Hieles are arguing, our focus. Okay, so we've shown that that is the case. There's another problem that I want us to look at. This problem comes with its own density and its own problems. Now, I chose this specific one because I want to talk to the geometric habits of mind before we actually talk about them. If we look at this diagram, let me just get my pen. If I look at this diagram, it says the following. In this figure, AB is parallel to DE. So immediately, that side is parallel to that. I call these visual mediators. I'm using visual mediators on my diagram to translate the statements that are given here. And DF is perpendicular to CE. Now the visual mediator for that is already on the diagram. It's over there. Now they go into the question. That's all they tell us. They tell us the lines are parallel and there's a right angle. Determine the perimeter of the triangle ABC and the perimeter of CDE, the bigger one. Explain completely how you found your answers and how you know that they are correct. Now folks, I want to stand still here. The moment we have parallel lines and we have what looks like, listen to my language, what looks like transversals. Remember, what is a transversal? A transversal is a line segment that runs from the one parallel line to the other one. It can cross it as well. But the key word there is it's a line segment. Well, let's unpack that idea. What is a line segment? Well, a line segment is a line which by its very implication implies that it's straight. In the geometry class, lines are straight. Okay? If I say line segment, ray, or what? Yeah, line segment, ray, chord even. I'm talking about something that's straight. If I say triangle CDE, the fact that I said it's a triangle CDE means it's made up of three connecting straight lines. So saying straight line in the geometry class is like saying, oh, that's a female woman, or that's a male man. It just doesn't make sense. Okay, so be aware of that. That's my first point. My second point is they have to tell us that this line on the diagram is a straight line and that is straight. And the way they could have said it is by AD is joint, BC is joint, and they intersect at C. Why is that important? Well, for vertically opposite angles to be equal in this diagram, it has to be two intersecting lines. Now, we don't have to have that. My point is here that I can have the one triangle. Now I'm going to try and draw one triangle here, and I could have had the other triangle lying just off, like that. This line is not a straight line. That is not straight. That is not straight. So we cannot say that those are equal to each other. So folks, as geometric teachers of geometry, this is the most incredibly important part of the geometric lesson is this paragraph over here. All the information that is in this paragraph gives you information that you need to answer the geometry question. Now, a lot of textbooks do not have that in their books. They just say AB is parallel to CE, show that this and that is true. Okay? They show it maybe with just showing visual mediators. But the point is still that you cannot function on Van Hiele level 0 in a geometry class in a high school environment. You cannot expect learners to assume things in the diagram because the diagram just doesn't tell them that. And people find it very hard to believe that textbooks can sometimes not have all the information that we need to be able to work with the geometric rider or the geometry. So let us pause at this point, and I want you to write out the proof, but now the purpose of that is for us to see how much knowledge condenses in this particular problem. So pause it, do the results, and then we'll talk about it. Okay, let us see what the semantics of this proof is, how dense the proof is over here. Now, first of all, we've got our visual mediators here. Now I need to look at where do I have information that I want. Well, the final product must tell me the perimeter there, so I need that side. Must tell me the perimeter of the big one, so I need this side, and that side. So I need to do a bit of work. I need to find the length of the 4 sides in this figure that is missing, the 4 sides that are missing. Okay, so let's see. Well, now we start working with our definitions that are formally there and the relationships that are in place. In this big diagram, the relationships that are in place only in that component of the diagram activates Pythagoras' thinking, because we have a right angle and we have 2 of the 3 sides. So we start off and we say, in triangle DFE. Okay, in triangle DFE, the following is true. I have angle F, which is 90 degrees. That was given to me. And that is key to acknowledge, folks, because if the 90 degree wasn't there, you cannot use any Pythagoras in that triangle. You also cannot use your trig ratios with right angled triangles. Okay, so we could do it in 2 ways. We can use trigonometry, find this angle and then find that side, or we can go straight for Pythagoras. The quickest way is Pythagoras. So he said EF is equal to the square root of 52 squared minus 48 squared. Now, our reason there is good old Pythagoras. Now, folks, if we calculate that, I'm just getting my notes ready so we don't have to use the calculator all the time. That becomes the square root of 400. And the square root of 400 is 20. Now we get into another habit of mind. And that is, once we have our results, we put them in the diagram. We now have that side. Okay, so we can now progress beyond the triangle and see what else we can find. If we move into the full triangle, we've got a problem. We only have that side in this triangle. There's 2 sides short. Let's see if there's anything happening there. Not at all. There's no right angle. We cannot say there's a right angle at A because it looks like a right angle. That's Van Hiele level 0. We're moving to the rest of the diagram, and we can see in this component here, if we want to work with that right angled triangle, there's 2 sides here that we have. We have that right angle, but we don't have these 2 sides. Sorry, we have only 1 side. So let's move across the diagram. If I look at the top little diagram here, I cannot assume that A is 90 because it looks like 90. That's Van Hiele level 0. I am at the formal deduction section or level of reasoning. So I need to have read that that's 90. So there's nothing that I can do in here. So let's move across the whole diagram and let's use the parallel lines. Now folks, this is the point where you should have read that this line segment intersect that line segment at C, because without that you cannot start arguing about the angles. So this angle here, I'm going to say, is equal to E over there. There's the parallel lines, there is the transversal. And the same for AC. This whole angle over here at D is equal to the whole angle at C. I could have also used the fact that those are vertically opposite. Now if you glance your eye across those two triangles, they are indeed similar. So what am I doing now? I'm moving into another set of theorems and rules and axioms and postulates and definitions related to triangles, and that is the shapes of triangles being the same. Okay, so let's move into triangle ABC and triangle, I'm just going to say CDE for now and talk about that habit just now. The following is true. AB is parallel to DE. That was given to us, and our arguments are going to rest on that fact, so acknowledge it. Okay, therefore, angle BAC, which I'm going to call angle A, belongs to triangle ABC, so I put it underneath there. And angle D in the bigger triangle are equal. I'll talk about the proof now, or the reasoning now. Angle B in the small triangle is equal to angle E in the bigger triangle. Now both of those are alternate angles that are equal. Why? Because those lines are indeed parallel. Okay, so I can now conclude I've got two of the three angles the same, the third one will be. So I can conclude that triangle AB, and the third angle is C, is similar to triangle, now DE. D corresponds to A, B and E corresponds, and the third angle in that triangle is C. Why is that the same? Because they are equiangular, meaning all the angles are the same. So I've drawn on similarity now. Now I can construct what I need. Let's say I want to find, let's go for CD first. I could have gone for any of those. Let's go for CD. If I want CD, I must use that. Then I must ask myself, well, if I use that, it corresponds to AB. AB I have. Okay, good. Then I want to use, or rather AC. AC is what I have, the first and the last. I also have AB. Okay, so I can use AB here. The corresponding side is DE, which is there, and I have it. Okay, beautiful. So we can do that. We can say that DC over ED is now equal to, and notice I put the DC at the top, so I don't have to manipulate. So this over that is equal to AC over AB, and the reason is the sides are in proportion. Why are they in proportion? Because the triangles were equiangular and therefore similar to one another. And all I need now is to substitute. DC is equal to AC, and AC is 15, all divided by AB, and AB is 13, and then multiplied across is AB. Now AB stays where it is, multiplied across is ED, which is 52. Now folks, if you calculate that in your head, not on a calculator, you'll see it is 60 units long. Now transfer. This is 60. We've got that. Okay, so now we can look at CF. So we go back. In triangle CDF, the following is true. According to Pythagoras, CF is the square root of the 60 squared minus the 48 squared. Now folks, if you work out 60 squared minus 48, you get 1296, and the square root of that is indeed 36 units. Okay, so we've gone Pythagoras, similarity, Pythagoras. Now we do have CF as 36, so it goes on. The last thing I need is BC. So for BC, let me just zoom out a little bit. For BC, I'm going to move across the triangles again. I want BC, so let me go there. So I'm going to say AC over BC. Okay, so AC over BC is equal to DC over BC means it's EC, is corresponding. And again, the sides are in proportion. So what does that mean? It means that to get to BC, BC is going to be, now BC is multiplying across, so DC is coming down here. So it's AC times EC divided by DC. We substitute in, we have 15 multiplied by 56 divided by DC, which is indeed 60, and our result there is 14 units. Now you will see I'm putting units down. So all that's left now is the perimeter of triangle ABC. You add, for triangle ABC, you add the 3. We've got the 14, 14 plus 13 plus 15 is 42 units, and the same for the perimeter of CDE. 60 plus 50 plus 56, and that gives us a total of 168 units. Okay, the point of this problem is to show you the necessary and sufficient information was not in that little paragraph that accompanies this geometric problem. Now we cannot accept learners to work with things that the necessary and the efficient has not been shown. The constellation of ideas here in this problem is we needed right angles, so we can use Pythagoras. We could have also used trigonometry alternatively. Okay, so Pythagoras was used. We worked across the diagrams. Unfortunately, we had to assume that lines are indeed straight to work across the diagram and work with the similarities of the triangles in the diagram. Let's return to our discussion over here. Okay, so we move on and let's see what Van Hiele says about the level of formal deduction. He says in his experience as a teacher of geometry convinces him that all too often students have not yet achieved this level of informal deduction. It is key. Consequently, they are not successful in their study of the kind of geometry that Euclid created, which involves formal deduction. Okay, so we need to, as teachers, afford them this opportunity so that they can get to this level of geometric reasoning. The last level that we want to talk about is the level of rigor. Okay, that's the final level of geometric reasoning according to the Van Hieles. Learners at this level understand the formal aspects of deduction, such as establishing and comparing mathematical systems. They can understand the use of indirect proof and proof by contrapositive, and can understand non-Euclidean systems. Now folks, we know that in the grade 11 book, or in the grade 11 curriculum, there are certain theorems that are proved by contradiction. If a child is not at this level, that type of proof will in no way make sense to them. So what can the student do at this level? They can compare axiomatic systems. Example, Euclidean versus non-Euclidean. They can rigorously establish theorems in different systems in the absence of reference models. Okay, now folks, if you look at spherical geometry as an example, everything that happens in the plane can transfer to the sphere, but the rules of the game changes once they are on a sphere. And at this level, a child is able to negotiate that transition quite successfully. So at the level of rigor, the learner should understand various arithmetic systems without having to revert to a visual model. The knowledge gained in geometry gives learners access to apply that knowledge in various situations, including those that are not in the planar space. Various forms of proof is understood and flexibly applied across contexts. Okay, now I've spoken about contradiction and contrapositive. This level is the level where learners solve geometric riders independently and can apply their knowledge to formally construct a proof. Now, as a teacher of geometry, folks, here you can go beyond what's in the curriculum. Read on. There are theorems about relationships of lines that intersect one another in a geometric shape, in a circle. Chords that intersect, the intersecting chords theorem, the tangent secant theorem. Throw those at the kids. Put the conditions in place and afford them the opportunity to construct proofs with the knowledge that they have about the object that they've learned so far. Okay, so that concludes our last video on the levels of geometric reasoning. In our next video, I will discuss the phases of learning, and after that we're going to talk very excited about Mark Driscoll's work in the geometric habits of mind. If you've learned something, please like the video, share it, subscribe to my channel, and feel free to comment and on the content of this video in the space below.